Okay, welcome everyone. Today is the last class of this semester for this course, and you guys already had your final exam on Monday. I saw that there are some questions or comments on the final exam, and there were also comments on why we are having this final lecture today after the final exam. So, of course, my philosophy is learning never stops. So it doesn't stop at a final exam, right? So if you're interested in a topic, you're interested in a course, or if you're interested in any kind of concept, it doesn't need to be this course. It can be any course or any topic that you're interested in. That's a continuous process. It does not stop at a final exam. That's what you'll see later in your life. But yeah, today what I wanted to discuss was, of course, the solution to the final exam papers and how do you approach these kind of problems. Of course, I understand that the questions in the final exam were probably a little bit on the harder side. That's what most of you may have felt, because the you'll also have to consider that, for example, question number 2 was almost similar to what you have solved in your homework number 8. So in that way, I try to ensure that all of you at least get that 70 marks right. And then, of course, the first question was probably something that some of you may have had a little bit of trouble with. So we'll discuss that in detail, that how to approach these kind of problems. Okay, but please do let me know if you think that you may have not done how you expect it to be in the final exam. But yeah, we can see if we need any kind of makeup test for that, because we still have time. Okay, so just let me know, and I will be in case you are interested in that. I will be happy to arrange for a makeup test for some of you who feel that okay, you could have done better, and it might affect the grades or anything like that. Okay, but yeah, as you know that I am generally pretty lenient with the grading, what you have seen in your exam number 1 and exam number 2. So please do expect that the grading will be done in a very similar way for this exam as well. Now, coming back to what we wanted to discuss in today's lecture was, of course, the solution to your homework number or the exam number 3. But at the same time, I also wanted to get some of your feedback on how you think this course went, what you learned, and what went good, what went bad, and things like that, because that will help us to improve the course better in future. And to that note, I posted an announcement today morning on the course evaluations. So please submit your course evaluations if you haven't done so. The final deadline to submit all these course evaluations is Friday. And of course, your evaluations will help us to make this course better in future semesters. Okay, so we are relying on you for that. All right. So coming back to this solution of your exam number 3. So what you have as the first question is basically you needed to find out transistor operating points, or the DC operating regions or DC operating points of the transistor. What do you mean by the DC operating regions or DC operating points? Is basically you wanted to find out what is the VDS and what is the V overdrive for, let's say, all transistors in the design. And we'll show how to do that. And many of you have done it right. And I was really, and I haven't checked all the answer papers yet, but many of you have already done it in the correct way that it should be done. So I was very happy to see that. Now, to find out the DC operating points for each of the transistors, or to make sure that all the FETs in the design are in the active region or in the saturation region, what you need to do is that you just need to find out what is the VDS and overdrives for each of the transistors, right? And this is something that you had done in your homework number 4, where you the amount of current was given, and from the amount of current, you just use the formula that current is equal to K over 2 times V overdrive squared, and you find out the V overdrive for each transistors in homework number 4. So this is exactly the same. So even though it might seem a little more complex because you have a differential circuit here, but the approach should be exactly the same. It should not be anything different. It's exactly the same as what you had done in your homework number 4. So in your homework number 4, the current was given. Here the current is drawn in the circuit that this is the bias current that you are using, and that is 100 microampere. So you should start at that point, that what is my bias current in the circuit. Remember that because this is a differential amplifier, you have this tail current source. So this is the current source that's connected at the tail of this differential amplifier, and that current determines all the DC points in the circuit, right? So you should start from that point that, okay, I know my current, that is 100 microampere, that is going through this M10 transistor, which is diode connected over here. So the drain and the gate of this transistor is connected together. So which means that the VDS will be equal to VGS. And you already know that this transistor will always be in saturation because it is diode connected. But what is the overdrive in this case? So the overdrive is, you can find that out from ID equal to K over 2 times V overdrive squared. ID is given, K is given. You just need to find out V overdrive. And in this case, the V overdrive turns out to be 0.2 volt. The VDS of this is equal to V overdrive plus VT, because VDS is equal to VGS for this guy, for this M10 transistor, because this is diode connected. So your VDS, the drain to source voltage, is equal to the gate to source voltage, because drain and gate are connected. Okay, so drain to source voltage is equal to gate to source, and gate to source voltage is overdrive plus the threshold voltage by definition, because the definition of overdrive is VGS minus VT. So VGS will be equal to V overdrive plus VT. So if you do that, you'll find out the VDS of this transistor is 1 volt. Of course, VDS 10 is greater than the V overdrive of 10. That means M10 is in the active region. Now, what is interesting in this circuit is that for all the transistors that you see, the overdrive will be same. And why is that? That is because you have this 100 microampere current flowing into this branch, flowing here. And it is mentioned in the question that all the transistors have equal W over L. So if all the transistors have equal W over L, you have, so remember that this part of the circuit is a current meter, right? So you have a current source on the left side, and you're mirroring this current in the two transistors over here on the right side. So if all the transistors have equal W over L, you know that the current through this transistor will be equal to the current through this transistor, will be equal to the current through this transistor. So the total current in the tail transistor is double of this 100 microampere, which is 200 microampere. But the way we are simplifying this is that we're saying there are two transistors in parallel. So each of them carry the same 100 microampere current, right? So that's, again, by definition from the current meters. And because the current in the tail transistor gets divided equally in the two branches, so 100 microampere current will flow here, again 100 microampere current will flow here. Now look at this top PMOS transistors. They are diode connected. So this is the drain terminal of the PMOS. This is the gate terminal of the PMOS. So this is diode connected, and the gates of these two transistors, so for example, M4 and M6, they are connected together. So again, this forms a current meter, right? On the left side, this forms the current meter. So because of that, you'll see the exact same amount of current flowing in the two branches of the differential amplifier. So those are 100 microamperes, but also the current flowing in this and the current flowing in this is also 100 microampere. So all the currents in the circuit are 100 microampere. There's no difference at all for each of the transistors. So each of the transistors are carrying ID equal to 100 microampere. Each of the transistors have a K of 5 milliampere per volt square. The PMOS and the NMOS both have a K of 5 milliampere per volt square. So the K value is equal, the ID value is equal. So the overdrive for all transistors in the circuit are equal. So if you catch that, then the rest of the thing becomes very easy, because just in a similar manner that you have solved your homework number 4, that from your ID you find out overdrive. From your overdrive, because you know the threshold voltage, you can find out what is VGS, and then you can find out all the voltages at every point in the circuit if you know the VGS. So that's what we'll do here. Okay, so in terms of the approach, this is exactly same as your homework number 4. Start from the current, because that's what determines the biasing conditions at each of the points. And just like in your homework number 4, again, you started from the current over there. Okay, so now if you want to find out what is happening for M1 and M2, that is the input transistors. So this is one input transistor, this is the other one. So again, look at this connection that is done from the output back to the input, right? So there is one connection that is made from the output back to the input, and the input, the original input is provided at this right-hand side M2 transistors. So if you just represent it with a black box, that yeah, you have a positive input, you have a negative input, you have some kind of output for this amplifier. And in this case, the output is only this output. So only one of the outputs we are taking. So it's a single output, but two inputs. The output is fed back to one of the inputs. right? So that is a unity gain configuration of an op-amp that you have studied before. And in the unity gain configuration, whatever voltage you have over here, the same voltage will be at this point because of the virtual ground property, and because the input and output are connected together, the same voltage will also be at the output. So you have your circuit over here, and you have your input at 4.5 volts, which means that your output will also be at 4.5 volts DC, and the other input of the differential amplifier will also be at 4.5 volts, just because of this unity gain configuration that you have over here. Okay, so both the inputs are at 4.5 volt. Also, the current through the devices is 100 microampere, which means that the overdrive will be same as the overdrive that you calculated over here, that is equal to 0.2 volts. Now, overdrive is VGS minus VT, so you can write that down. This is VGS minus VT, that's equal to 0.2 volts. You know the VG, you know the gate voltage at the input transistor. The gate voltage is this 4.5 volts. So if the gate voltage is 4.5, source is unknown, and the VT is 0.8 that is given. On the right-hand side, you have 0.2 volts. So you can find out what is the source voltage. So the source voltage of the M1 or M2 transistor, which is this point, that is, even though that's an AC ground. So some of you may have made this mistake that you call that a ground, for virtual ground, but that's a virtual ground property is something that holds true for your AC, right? So in terms of DC, that should not be a ground. If this is a ground and that is a ground, then the VDS across these two transistors becomes 0. That means these two transistors going to triode, and your circuit will not work. So in terms of DC, this is not 0. Virtual ground means that this point has an AC potential equal to 0. Okay. So you can find out what is your VS. That's the source voltage of transistors 1 and 2. That would be the drain voltage of transistor 5. Because the source of transistor M1 or M2 is same as the drain voltage of transistor M5A or M5B. So that becomes the VDS5. Also, at this point, you can note that the V overdrive of the transistors M3 and M4, the V overdrive of these two transistors are also equal to 0.2 volt, right? It's the same overdrive all throughout the circuit. So the V overdrive of M3 and M4 is also 0.2 volt. And then you can expand the V overdrive of the PMOS transistors as VSD minus absolute value of VT. That's 0.2 volt. Again, VSD is equal to VSD. VSD of the PMOS transistor, source to gate, is equal to the source to drain, because drain and gate are connected together. It's a direct connected transistor once again. So VSD can be written as your VSD of 3 and 4, and that will be equal to this 0.2 volt plus 0.5 volts, so that's 0.7 volts. So the drain to source drop or source to drain drop for the PMOS transistor is 0.7. Remember that the source of the PMOS transistor is connected to VDD, and source to drain drop is 0.7 volt. So this point, this output of the differential amplifier or the drain of M3, M4, M1, and M2, those points are at 4.3 volt, because the source to drain drop is 0.7, source is at 5, so the drain has to be at 4.3. So the drain voltage of transistor 1 and 2 are also at 4.3 volt. You can find out what is the VDS of transistor 1 and 2, because you have already found out what would be the source voltage of transistor 1 and 2. And you found out what would be the drain voltage of 1 and 2. So the difference of those two is 0.8 volts. And that is higher than the overdrive. So transistor M1 and M2, they are also in the active region. M3 and M4, you have already found out that the VSD is 0.7 volt. Overdrive is 0.2 volts. So this is also inactive. M5 and M5A and M5B, you have already found out the VDS of 5 is 3.5 volt from here. The VDS of transistor 5 is 3.5 volts. The overdrive is equal to 0.2 volts once again. So this is also in active region. Okay, so now you have completed all the transistors that are in the differential branch. So you have completed everything that's within this differential circuit. We are left with the transistors that are on the sides, that are on the left side or the right side in this diagram. But you already know some of these voltages. For example, you know that this voltage is at 4.5. You know all the overdrives of these transistors are 0.2. That information is already there with you. So if you want to find out what is happening to M9, So M9 is this transistor, because this transistor establishes the current mirror, the mirroring between this leg and the right-hand side leg. Okay. So if you want to find out what is happening to the M9 transistor, your V overdrive is 0.2 volt. From that, you can find out what is your VGS, that is 0.2 plus the VT. So VGS will be equal to 1 volt, and VGS equal to VDS because that transistor is also diode connected. If you go back, this transistor is diode connected. So VGS equal to VDS, which means that you can find out your VDS to be equal to 1 volt, and that is higher than overdrive. So M9 is also in active region. What is happening to M7? M7 is basically the mirrored current or the mirrored transistor that you see on the right-hand side. So that is also carrying the same current, so basically the same overdrives, and you can write down the V overdrive as 0.2 volts and VDS7 to be 4.5 volts, because you know what is the voltage at the drain of this transistor, that is 4.5. What is the source? That is at Z. So VDS is 4.5 volt and V overdrive is 0.2 volt. So again, M7 transistor is also inactive. M6 transistor, that is the transistor on top over here. If this is 4.5 volt, then the VSD drop across this transistor is 0.5 volts because VDD was 5 volt. So your VSD is 0.5, overdrive is 0.2. So this transistor is also inactive. Okay. And finally, M8 transistor, that is the transistor that you see on the left-hand side. So for this transistor, again, the overdrive is equal to your 0.2 volt, and VSD is equal to VS minus VD. VS is at 5 volt. VD is something that you have already found over here, because the drain of the M8 transistor, the drain of this M8 transistor is this point, which is same as the drain of the M9 transistor. So you already found that out. So the VSD in this case is 4 volts, which is higher than overdrive. So M8 is in active region. So all the transistors that you see here are in the active region. What will happen in part number B? In part number B, you are reducing the input voltage to the M2 transistor or the input voltage to the circuit. So now here you'll see, if you go through the solution, you'll see that we are following the same approach, but we already know some of these things, that the overdrives are already 0.2. Many of these things will not change. For example, let's say I'm using the same approach. If this is 1.1, this will also be 1.1. This will also be 1.1. So those are the values that are changing. But again, to make sure that you have the same V overdrive, which means that you have the same VGS between this point and that point, the source voltage here will reduce. So this is the same concept that you used during designing of the op amps or during design of the differential amplifiers, that if your input voltage reduces, if your Vin to the gate of the M1 or M2 transistor reduces, because you still need to draw the same amount of current, the VGS of M1 and M2 transistors should remain same. So if gate voltage reduces, the source voltage also has to reduce. You can also do it mathematically and find it out mathematically, as we have done in the previous part, what I'm showing over here as well. But just intuitively, you can say that as your input voltage, as your VG is reducing, since your current is same, the source has to reduce, because the definition of current is equal to K over 2 times VGS minus VT whole square. Okay. So by definition, if your current is same, if your gate voltage is reducing, if your threshold is same, so the source voltage has to reduce by the same amount. So here the source gate voltage is reduced from 4.5 volts in the first scenario to 1.1 volt to the second scenario. So you have a reduction of 3.4 volts. So the source point over here, or the drain of M5A and M5B, that will also reduce by exactly 3.4 volts. Because of this equation, that current remains same, that means VGS has to remain same. Whatever change you see in gate, it has to be the exact amount of change in source. And if that is true, you already found out what is that source potential in the previous scenario. That was 3.4 volts. That needs to reduce by, that was 3.5 volts, but now this needs to reduce by 3.4 volts, because that's the amount by which you're reducing the gate. So your source also needs to reduce by the exact same amount. So your Vs will become 0.1 volt if you reduce this by 3.4, and 0.1 is less than 0.2, which was your overdrive. So now your M5 transistors will go into triode. So that's the only difference you'll see in terms of the active regions or the saturation regions of the transistors. All right. So now that you look at it from the perspective of overdrives, and overdrives being same for all the transistors because current is same, and you use this concept that because the current is same, if you change the gate voltage, the source also needs to reduce by the same amount. You'll know that which transistor goes out of saturation as you do that. Okay. So for future, maybe you can try building these kind of intuitive understanding of the circuits, even without solving all the points. Yeah. So for example, for problem number 1B, you could have just guessed from the concept that okay, the source voltage also needs to reduce for the M1 and M2 transistors, and you'll know which transistor goes out of saturation in that case. Okay. So try to build these intuitions around it. Of course, it may not happen within a single course, which is like 4 months, right? So you guys learned about MOSFETs, you guys learned about the equations of MOSFETs. Now we are trying to do very complex circuits with MOSFETs. So of course, that doesn't happen in a semester. I definitely understand that, but for future, try to build these kind of intuitions. But in spite of saying that, some of you have already done this problem correctly, and kudos to that. The second problem was very similar to your op-amp design problem that you had done as your homework number 8. I would say the only difference is that you have a VSS which is minus 2.5 volt. Right? So that is probably the only thing that you need to consider here, which is different from your homework 8 problem. And if you're considering that, then everything else will become very simple. So you can just find out, just like you did for homework number 8, you can find out what is your CC, what is your I5, and I have given the steps as well. That okay, this is the step-by-step solution that you should do for this problem. So find out CC, find out I5, find out what would be your W over L of 3 and W over L of 4 using I5 and ICMR max value. Again, just like your homework number 8. Next, you can find out W over L of 1 and W over L of 2 using CC and GBW. Exactly same as what you had in your homework number 8. No difference at all. Now, finding out W over L of 5 using the value of I5 and ICMR min. Here, there would be a slight difference. And again, most of you, I think almost all of you have done it correctly, that your VDS of transistor 5, as you're trying to find out the W over L of 5, the VDS of transistor 5 is VD5 minus VS of 5, right? VDS is VD minus VS. And in this case, the source voltage of transistor 5, which is this transistor, the source voltage of this transistor is at VSS. And VSS is minus 2.5 volt. So this is the only thing that is different from your homework 8 problem. That instead of VDS5 becoming just VD5 for your homework 8, in your homework 8, VS was grounded. So VD will be exactly equal to VDS. But in this case, VD is not equal to VDS because VS is minus 2.5 volt. So if you just consider that and do the same calculations as you have done in your homework number 8, you'll come up with the correct W over L of 5 for this transistor. Okay. W over L of 6 and 7, exactly again the same method you had followed in your homework 8. There's no difference at all. And you can find out what would be your omega W over L of 6 and 7. Checking if your Vout min is really less than minus 1.5 volt, because that was one of the specifications given in the question, that your Vout min has to be less than minus 1.5 volt. And in this case, again, if you wanted to check that, your Vout min, what would be the minimum output voltage? What would be the minimum output voltage at this point, at the final output? The minimum output voltage is basically the voltage that you have at the source plus the drop that you have across the M7 transistor. Again, in your homework number 8, this voltage at the source was 0. So whatever drop you had across this M7 transistor was your minimum or was your output voltage. Now, whatever minimum drop you can have across this M7 transistor will be your minimum output voltage, right? The minimum value of this drop, if this VSS is 0, the minimum value of this voltage drop will be equal to the minimum output voltage. So what is the minimum value of that voltage drop? You already know from your ID versus VDS graph is that this is the saturation region, right? When does the transistor enter saturation? When it's at this knee point. And at that point, VDS is equal to V over drive. If VDS is more than V over drive, you're in the saturation region. If VDS is less than V over drive, you're in the triode region. So the minimum value of VDS that you need to ensure over here is basically the overdrive. So if you already found out the overdrive voltage from the currents and the K values, just like you were doing for problem number 1 as well. So if you have the overdrive for this transistor, you can find out what is the VDS, minimum VDS for this transistor. Now, of course, instead of this source voltage being 0, in this case, the source voltage is VSS, which is minus 2.5 volt. So you'll have to shift the output by that much amount. Okay. So if you do that, I'm just writing down the equation over here that the minimum V out minus VSS. So this is the amount by which you're shifting it, because you do not have a ground, you have a minus VSS at that point. And that would be equal to VDSAT, or the minimum value of VDS, that you can find out from the current values and the W over L values that you have already calculated. And you can find out that this drop is 0.68 volts. If the drop is 0.68 volt, what is the absolute value? The absolute value is minus 1.82 volt. Because if this point, if let's say point A is at minus 1.82 and point B is at minus 2.5, then the voltage drop across those 2 points is basically 0.68 volts. That's what you have found out here. So minus 1.82, definitely less than minus 1.5. So you can verify this. And you can verify the gain and power consumption, again, according to the same formulas that you had used for your homework, with the slight difference that for your power consumption, it's the voltage difference across the 2 points, through the 2 points where your current is flowing, that's across VDD and VSS, times the amount of current that you consume. So it's VDD minus VSS times the total current that you consume. Since VDD is 2.5, VSS is minus 2.5, you have a 5 volt over here, and your I5 current is 30 microampere, your I7 current was around 230 microamperes. So total power you can calculate to be around 1.3 milliwatts. Okay. So yeah, I think that's about it. So your question number 2 was very similar to your homework 8 problem, whereas question number 1, apparently it looked very different from what you had seen before. But once we go through the solution, you see it's the exact same approach that you followed for homework number 4. So as you solve any kind of real practical circuits in later semesters or during your internships, just make sure that you are following the same approach. So focus more on the approach that, yeah, if I'm talking about the biasing, the DC biasing of the transistor, start from the current, try to find out the voltages at each point so that you know that what is the value of VDS and V over drives. That will make things really simpler if you follow a logical step-by-step approach. All right, any questions over here? Yeah, Michael. These 2 branches or these 2? These 2 branches. So that's the property of the differential amplifier, right? So remember that if you have this, oops, sorry. If you have, let's say, this single current source at the tail, and you have 2 input transistors, and if you have 2 load resistors. So that was the basic structure of the differential amplifier that we studied in the beginning, right? So in the scenario when the DC voltages or DC potentials of these 2 transistors are same at the gate. So let's say this is VG1, this is VG2, right? Those are the 2 gate voltages. What is the source voltage for each one of them? The source voltage is common. So let's call that V source. So that's a common source voltage for transistor M1 and transistor M2. So what is the VGS for each of those transistors? VGS for the M1 transistor, it's VG1 minus VS. For M2 transistor, it's VG2 minus VS. So these are the 2 VGSs for these 2 transistors. Again, what is the formula for current? Formula for current is equal to current equal to K over 2 times V over drive squared. Because the VGSs are equal, so if your VG are equal, if the gate voltage is equal for these 2 transistors, if the gate voltage is equal and the source voltage is always equal because that's the same point, so your VGS is same, that means your V over drive is same, that means the current flowing through these 2 transistors are same. Now, according to KCL, where does that current go? That current gets added at this point and flows through this current source. So whatever current source you have over here, half of that current will flow through the left side branch, and half of that current will flow through the right side branch, given that your VG1 is equal to VG2. Okay, so that was the basics of the differential amplitude. Does that answer your question? Oh, why the VDSs are equal? That's what you're asking, right? That this is 4.5 volt, but how do you find out that this point is also 4.5? Is that the question you're asking? Okay, okay. So that goes back to this theory that, okay, if you have an amplifier, let's say 2 inputs and 1 output, and if you feed back this output to the negative terminal, that becomes a unity gain feedback, right? Again, think about the op-amp circuits that you had studied during your maybe homework number 2 or 3 and during your exam 1. So this is a unity gain configuration, right? So in your unity gain configuration, what you really have is, if this is your input voltage, the output voltage, this point, the voltage at the negative terminal as well as the voltage at the output will be same, right? So if this is V in, at the output side, you'll also see V in. Let's
Give me my test.
All right. So that's the definition of a unity gain configuration, that whatever your input is, at the output side, you'll see the same thing. And because this output and the other input is connected together, you see the same voltage here as well. So that's why if this is 4.5, that is 4.5, and this is also 4.5. Now you may ask that, how do I know that this is positive terminal and this is the negative terminal? Right? So for that, you have to look at the structure. So for example, this is effectively a common source amplifier, right? So there will be a 180-degree phase shift between the input and the output. So maybe let me draw it with a different color. So between the input and output, you have a 180-degree phase shift. That goes to the input of this PMOS transistor, and this is here, the output is for the final stage. Again, there is a 180-degree phase shift between the gate and the drain of this common source. So what is the difference, phase difference between the input and the output? It's 0 degree, right? There is 180-degree phase difference here, another 180-degree phase difference here. So 180 plus 180 makes 360, or 0 degree phase difference. So your input over here has the same phase at the output over here, that according to your definition of the op-amp, right? In the definition of the op-amp, the phase over here was equal to the phase over at this point. So you know that this is the positive terminal and this is the negative terminal, because if you apply your input at the positive terminal, your output does not get inverted. So that's why this is the positive terminal. Your output does not get inverted over here. If this is something you had used for as your input, output would have been inverted. All right. So yeah, I think that's about it for the homework, for the exam problem. Now you probably already know that I have extended your homework 9 deadline to next week, and homework 10 is something that is an optional one. Again, if you wanted some extra credits, you could submit the homework number 10 over there. Now to solve homework number 9, I saw that there were a few questions. I guess someone was asking that they converted the input, or let's say, okay, so someone was asking that if I convert this function that I want to represent, that I want to design using my CMOS transistors, so this is the function y equal to, for example, let's say A and B or C wholly inverted. So someone was asking, do I need to represent it in terms of NOR and NAND gates, and then draw the NOR and NAND gates to come up with the final solution? So functionally, that is a correct solution, yes. That if you just represent this function as a combination of NAND gates and NOR gates, and then draw those NAND gates and NOR gates accordingly, and draw the internal circuits of the NAND gates and NOR gates, it's functionally a correct solution. But you'll see that you'll be using so many transistors in that case that it will not remain an efficient solution. So of course, you might get full credit for that. But for example, here, let's say this was the function, and we saw the implementation like this in the class. And how do you implement this? You first find out what is your y bar, and your y bar becomes A ANDed with B or C. So the represent of A ANDed with B and B or C is that because B or C, this is what you have in the in this part of the function. Because it is B or C, you'll present your or you'll place your transistors which are connected to B and the transistor that is connected to C. You'll place those two transistors in parallel, because the current can take either this path or that path. That is basically an OR function. So don't think about the digital OR function. This is analog OR function, that the current can take the left-hand side path or the right-hand side path. Right? So only with one single transistor, you can represent each one of them. So with two transistors, you're representing that OR function. So if you needed to represent a full OR gate, consider how many. So for example, NOR gate takes this 1, 2, 3, 4, and then you also need to place an inverter over here to make it OR. So an OR gate will need 6 transistors. Correct? Here you are representing the OR function with 2 transistors. Instead of drawing the OR gate, right? You are just representing it with the transistor. So it will be a valid solution if you do like your Y is equal to A ANDed with B or C whole bar. So you can write that as, for example, A bar ANDed with B, C bar. So here now you might say that this I'll do with a NOR gate, because it's B or C whole bar. So this is a NOR gate, and then I'll be ANDing the result with A bar. So that's also a valid solution functionally, but you might be using 20 transistors for that. So that's not an efficient solution. The efficient solution is this one, where you represent the OR function with parallel transistor and the AND function with series transistors. Okay. So that's what I would like you to learn through this exercise of homework 9. But of course, the other solution that some of you talked about, that I can just represent this arbitrary function. So for example, you had this arbitrary function over here, right? A or B ANDed with C or with D. So you can represent it as a combination of NAND gates or NOR gates, AND gates, OR gates, all different kinds of gates, and draw the internal structure of the gates. But again, you'll see you'll probably use 30 transistors in that case. Yeah, instead of 8 or 10 transistors that you'll need if you're representing it efficiently. So just to give you some estimate that, okay, this is what the circuit will eventually look like. That if this is your function, you have A or B ANDed with C or with D. So if you are representing the pull down network, which is over here, so this is your pull down network. For that, you are interested in E bar, what is the expression bar, and then it will be A or with B ANDed with C or with D. So this D will be a completely parallel path, because that's the final OR operation. A ORed with B, so that's this parallel operation between A or B. That needs to be ANDed with C, so C will be in series. And then this entire thing will be in parallel with B to make sure that your pull-down network is completed. So that's what you'll need for the pull-down network. Pull-up network will just be a dual of the pull-down network. So in that case, you'll have your A or B, they were in parallel, now they will go in series. C was in series with that structure, so now C will be in parallel with the A ANDed with B, or the series combination of A and B. And then D will be a separate series combination, because here D was a separate parallel combination. So it's just a dual of what you are drawing in the pull-down network. Okay. Now, to find out the R-on of the individual transistors, you can find out what would be the R-on of N and R-on of P, given that all the K values and the threshold voltage values are given, right? So you can find out what would be the on resistance of the NMOS and PMOS transistors. And keep in mind that this R-on is not 1 upon lambda ID. That is true in saturation. That is true for analog circuits. For digital circuits, R-on is basically the resistance in triode, which is basically 1 over K times VOV. Something that we had proved in class. I'll not go through the proof once again, but please go back to the relevant lecture and see why R-on is 1 upon K times VDD, or basically VGS minus VT in this case. Okay. Now, for answering the second part of the question, it is asked that, okay, if your VA, VC, and VD, they are turned on or they are connected with VDD, and maybe one of the other inputs is connected to 0. What will happen? So the easiest way to solve these kind of questions is that you consider, for example, here your pull down network, that you consider whenever the transistors are on. So let's say VA, VC, and VD, they are on. So VA, VC, and VD, these transistors are on, and VB, this transistor is off. So you just disconnect this from your entire circuit. So what you have is C and A, they are in series, and in parallel you have D. So C and A, the R-on of those two will come in series, and in parallel you will have the R-on of B. Okay. So you calculate what is the overall combination of that resistance. That would be, let's say, around 31 ohms. You can find out what is the RC for the pull down network over here. Okay. Similarly, in the other scenario, when all of them are 0, now of course, what is all the more important is that in the previous scenario, since VA, VC, and VD all were connected to high voltages, in the PMOS, in the pull up network, this transistor will be off. VC transistor, this will also be off. VD will also be off. If these three transistors are off, the output cannot charge through from VDD because the D transistor is off. So you are having an open circuit in the pull-up path. So the transistor, the final output will not charge. It will only discharge in this case. And you can find out what is the discharging time constant by doing this RC calculation. Okay. On the other hand, in the second scenario, when all the voltages were 0 volts, so because all the voltages are 0 volts, you know that all the PMOS transistors will be on. So this is on, that's on, this is also on. On the other hand, NMOS transistors are off. This is off, that's off, this one is off, this one is also off. So you'll only charge, but you cannot discharge in the second condition. Okay, so you see that here everything is open circuited in the pull down network. So you're only charging up, and for charging up, you'll just use the R-on P resistances, which are 75 ohms, and the series and parallel combinations of those, according to the way they are connected as transistors. So that would give you an RC value, and again, you can find out what will be the time constants. Okay. So that's how you'll solve basically this problem. And problem number 2 will also be very similar. You need to find out the R-on resistance and basically the value at which your output voltage could be minimum. Okay, any question here? So again, just as we part for this semester, that whenever you are looking at any circuit, maybe the circuit is very complex, but try to think of it in terms of what you already know. So you'll see that many times the divide and conquer based approach works best. That you just divide in terms of what you already know, that, okay, I see a common source amplifier somewhere. I see a common gate amplifier somewhere. And then try to think of them in terms of black boxes, that how those common source black box is connected to the common gate black box, how you have a source follower somewhere connected, and things like that. So always, if you try to take a simplified approach in circuit design, it helps. Do not try to go for, let's say, exact calculation up to 5 decimal places. That never helps. Right? It will take you an hour, but you will not get any kind of intuition of what is happening in the system. So good to get that intuition, do a divide and conquer based approach, try to find out what you already know, and try to use that knowledge to solve that circuit. And as you solve more and more circuits, you'll see in future you're becoming better at it. And you can, just by looking at a circuit, you can intuitively say what is happening inside it. So that's why, if you want to be a circuit design engineer, you can probably follow that approach and it will work out best. So I know many of you are interested in doing internships or full-time jobs in, for example, TI or analog devices, Intel, Apple. So all of them look for these kind of qualities in students, that whether they are trying to, or whether they are able to solve a question in a small amount of time. They never want 5 decimal places accuracy, because that never happens in real circuits. All circuits have some kind of tolerance, some errors, and you have to consider that there is a error tolerance whenever you design any circuit. Whatever you calculate, your final result might be 5% off or 10% off from that result. So there's no point calculating or doing the calculation up to 5 decimal places. It's much more important that you develop an intuitive understanding so that you can solve it approximately within a very small amount of time. So that's what all the companies want, that looking at a circuit, how fast can you say that how should the circuit behave? They do not want the final result up to 5 decimal places. Okay, so that's something just keep in your mind when you're preparing for any kind of internships with these companies. Any other questions? Yeah, please. Great question. So I think this is eCircuits 1. So eCircuits 2 is somewhere you will learn more about, for example, frequency response of an amplifier, the frequency response of individual transistors, noise in a circuit. So we didn't talk about noise or interference here, right? But in your lab, you saw that every voltage that you take a look at in your oscilloscope, there is some noise on top of it. So what is the theory of noise? How does transistors are affected by noise and those kind of things? So that is covered in eCircuits 2. So that would probably be one of the highest undergraduate level classes you can take as a progression of this particular class. But if you become more and more interested, there are a few graduate level classes as well. So if you're doing an integrated master's, for example, some of you might be doing that, then you can take maybe analog IC design 1 or analog IC 2 as natural progressions of that. So after this class, I'll probably suggest eCircuits 2. And then if you still feel that you're interested and you want to learn more and more, go for analog IC1 or analog IC2. If you're interested in application, so there is a very interesting class that will be course that will be offered in next semester, neural interfacing technologies. I think I had made an announcement regarding that. So it's an application of all these analog circuits for biomedical applications, specifically for neural interfacing. That, okay, some of you might know about brain-machine interfaces. So for example, what Elon Musk has been doing in his company called Neuralink, that they're trying to interface circuits with the brain so that it can help patients who are suffering from, for example, Alzheimer's, Parkinson's, or many other neurological diseases. Right? And of course, we need to understand the human brain better. So that's the research aspects are also there. So if you're trying to interface with the brain, what kind of circuits do you need? And you'll see that most of it will be the analog circuits that we have learned. You'll need some kind of amplifiers, you need filters, and you need signal processing circuitry, and so on. So out of that, in eCircuits 1, you are learning about amplifiers mostly. eCircuits 2 also teaches you a little bit about filters. So amplifiers and filters, these are probably most important things if you're considering any kind of analog signal processing or analog circuit design jobs, or if you're trying to go for further or more complex or more advanced courses on that. So any other questions? If not, have a wonderful rest of the semester, have a great holidays, and best of luck with your finals week. Thank you.